But the three main topics for us this afternoon, I picked only three because I could have talked about transport capacity and supply and bed forms and sediment plugs and many other things. But I limited this to these three topics because I think will be beneficial to most of you. Incipient motion, CMAP and CMAP 2P, and then mud flows, debris flows. So the focus will be on the latter part there, mud flows and debris flows, which I think is of interest to many people here in the Western United States. Incipient motion, I picked this topic to illustrate some of the issues and concerns that Professor Ettema explained this morning, that we know a fair number of things as engineering practitioners, and experience teaches us a lot of do's and don'ts and whatnot. But at the same time, there's a lot of things we assume and take for granted, parameters and so on, and we assume and dump this in the model and calculate and don't mind about this thing. And I know that for practitioners, consultants, and federal agencies, you don't have too much time to spend into fundamental research. But in academia, we feel it's our role at times to take some issues and really delve a little deeper into those topics. And incipient motion is one of them I want to illustrate this afternoon. So incipient motion is the beginning of motion, and a rule of thumb, like my 1,000 tons per square kilometer per year, is 1 millimeter of grain size requires a shear stress of 1 Pascal. So I like the SI system of units, and 1 Pascal, gamma HS, gamma 10,000 kilogram per cubic meter, and H of flow depth and S the slope. Multiply this, you get directly your shear stress, and then you can figure out more or less at what size of grain size is going to be at incipient motion. So this is a very nice little rule of thumb, and we assume from the Shields diagram that was from Shields directly here, Reynolds star, and then the tau star parameter, we called it the Shields parameter nowadays. And we get this nice graph if you expand the database there. We get values for coarser grains from sand and gravel and up there. We assume this value of this parameter, that's 1.1, 0.03, 0.06, and some people, some researchers said no, it's 0.03, and others said no, 0.06, and it's kind of school of thoughts, a bit like the color of ties that we wear. There are fashions in schools and also regionalism. This river will have critical shear stress 0.03. But my point here is that you need to go to the fundamentals, at least for us in academia, to look at where does the Shields parameter comes from. This shear, the applied shear over gamma S minus gamma ds. Well, it comes from the ratio of two forces. You have the drag force applied on it, the shear times the grain size, and then you have the weight that's going to be the submerged weight, the weight of the particle, with gamma S times the grain size, the volume, and minus the buoyant force, gamma times the volume of the particle and whatnot. And we just take the ratio of those two. There's a ds squared that cancels out here. That's the volume, that's an area. And we just take this thing here, and that's it, right? And we convert that shear stress into a shear velocity, which is by definition tau divided by rho, square root of tau divided by rho, which is GHS. So then we have depth and slope, and then you have the shear velocity. That is a parameter that will come back today in my lecture as being one very important parameter for determining bed load, suspended load, and so forth. But the key problem here, as I see it, is that we forget the lift force. There's a lift force being applied on the particle, and we totally ignore it. We assume that all particles, and that was the idea of Shields at the time, you had particles of the same size on both sides. So we said, well, it's one among so many particles, all uniform grain size. And then we'll just say, well, it's the same thing no matter what, so we can neglect it. And that's what we've been doing for a very long time. And therefore, we get values here, 0.03, 0.05. Remember that little box is going to come back in a minute or two here. So we assume that this is the case, but in theory, we know that, well, we don't have the lift force on it, and that's no big deal. And the other big parameter that we see in incipient motion is the angle of repose, that you dump material off a dump truck and you measure the angle at the base of that accumulation of material on the ground. And that's an old graph from Daryl Simons, actually, from his PhD dissertation. And there have been modified versions of it, but essentially as function of grain size in inches or millimeter, they're going to get a slight increase of that angle of repose from 30 to 40 degrees. If the material is very angular, kind of crushed material from a crusher, then you may have higher values for finer grains and so forth. So depending on the angularity of the material, you may get slightly different values and so forth. And we commonly use just one value and say, well, that's it, 35 degree, and don't worry about the rest. But in reality, incipient motion is not a ratio of forces. I showed you the ratio of forces, tau divided gamma s minus gamma ds, but it is a rotational phenomenon. So incipient motion, if this is a contact point that you hold in place, you don't let it go, then it's going to happen when the center of gravity is vertically above C. If G is to the right of C, that particle is going to topple. And if it's to the left of C, it's going to stay put. So we can look at this triangle, equilateral triangle here, 60 degree at the base. Of course, center of gravity is going to be at 30 by symmetry here. So therefore, you have 30 here at the base, so you get 60 to go vertical here. So that angle of repose should be 60 degrees, right? You can do the same thing with a square, so a little square or a cube. So you're going to say, well, I split this 90 degree in two, I get 45 at the base, so I need to 45 to bring this vertical. So now you get 45. You can repeat a pentagon and hexagon and so forth, and you end up with spherical particles that are going to have an angle 0. I mean, you put the bead on the table top and you slightly lift one side and the bead is going to roll to the other end, right? So it's very easy to mobilize. So you can see that the angularity, as you go to the left here on this scale, if you increase the angularity of your material, you increase the angle of repose, and therefore that makes a lot of sense. I said it's 0 for a sphere. Yeah, sure. Let's look at cylinders. If I put 3 cylinders together and they have the same diameter, then they'll have 60 degrees at the base, so you get 30 degrees to go to bring this particle on top there. Make sense? Yeah. Well, but if the cylinder on top is smaller than the 2 below, now that angle is going to be higher than 30. You see that? So it means the angle of repose is not a property of the particle. It's a property of the particle in relation to what it is standing on. Does it make sense? Yeah. So now if I put a big bead on top of smaller ones, then this angle would be less than 30. If I do the spheres, for instance, I put 3 spheres at the base and 1 on top, then we can calculate this by geometry and whatnot and get a little formula. Or if it's placed on top of 4 at the base and 1 on top, you get slightly different values of that angle of repose, yeah? So this angle of repose is very important for incipient motion. So if I place cylinders here, for instance, one on top of the other here, ratio 2 to 1, right? So the R1 is 2 times R2. So that tangent phi is 60 degrees, and you can calculate that the critical shear for this particle is going to be less than tau c for the bigger one, yeah, because it's on top. And if you get a big particle on top here to the right, now the tau c is going to be 2, is going to be a little bit bigger, but not twice, yeah? So that led us to the idea of going to the lab and testing this thing, because I was thinking if you go bowling, you can get the big ball there and get this to roll on 100 feet, and there won't be any resistance to this thing to roll, right? So we did a little program in the 90s at CSU. We got some plates. You see the plates here. We glued some particles of determined grain size on them. So we get one roughness, 1 millimeter, and the other one, let's say 3.4 and so forth. And we pick different beads. So we get some, marbles of different sizes, much bigger than the roughness size. And we get some steel ball bearings, and we get some particles from the backyard, right? Really with natural particles and so forth. And we put them on a test in the lab there over about, 3 meters or something like that of length. And we measured the rolling of particle one by one. So stopwatch there would take 10, 15 seconds to go from point A to point B. And we repeated this 10 times. And we took the highest and the lowest out, and we just took the mean of the rest. And we proceeded with that. So overall, we get conditions, different flow conditions, different ratio of the diameter of this one to different the bed roughness sizes. And we get about total of 10,000 particle velocity. So you get a big database there to play with and look at the incipient motion for those conditions and look at the velocity of those particles. And what we found is this. So you have a particle now of grain ds of a roughness bed of ks, which is different, could be the same. So if it is the same, then the ratio of ds to ks is going to be 1. And in this case, you remember my little box here, 0.03 to 0.06 on the Shields parameter. The Shields parameter for the particle that is on top here. Does it make sense? Yeah. So what we found was astonishing is that, yes, that is true for those particles the same size. But if I have a big boulder rolling on sand bed, and the sand bed is pretty plain and solid, then that particle can move. And we have the velocity here, velocity of the particle divided by that U star I was talking about. So 4 is the dark one here. So the particles are rolling. They are moving. And if you get between 6 and 8, well, they move, but a little higher here. Does it make sense? But those particles are rolling at the Shields parameter that is about 10, 15, 20 times lower than the 0.03, 0.06, meaning that if you blindly apply the Shields parameter to big particles on a smooth bed of smaller particles, you're going to be off tremendously, meaning big particles can roll on smooth and fine-grained surfaces. And this concept will come back when I talk about debris flows at the end of my presentation this afternoon. Another thing that we found, and that's why experimental research is really interesting. I give you one example here, but it could be about all kinds of other parameters that we assume blindly, and they could be revisited. Interestingly, if you want to get the velocity of the particle, I normalize by U star, which is a hydraulic parameter that is constant. But VP is my velocity of the particle. I get better agreement, and that's the graph here, if I take the Shields parameter of the particle down below, then the Shields parameter of the particle rolling on top. Does it make sense? Yeah. And you find here that at those star, remember I said 0.03, 0.047, this should normally be the Shields incipient motion, and you still have particles moving at 7 times the shear velocity for those conditions. And you can get incipient as low as 0.004, for the Shields parameter. So my point is not really about this topic per se or incipient motion as much as it is the idea that we think we know a lot, and we do know a lot, and the experience and practitioners, teach us a lot, but there's still a lot of room for fundamental research in any of the fields that we are dealing with, and assumptions that we blindly dump into a computer program to calculate a number of things. And I feel that's the role of academic and professors, to look into those problems. And I will also illustrate the importance of this later on, like I said, when I talk about debris flow. Okay, my second topic is CMAP and CMAP. I have to praise the US Bureau of Reclamation for leading the understanding and also the analysis of the modified Einstein procedure. I mean, dating back to Colby and Hembury, Lara and Pemberton, Ernie Pemberton did some work. The Bureau has been involved in the development and understanding of the modified Einstein procedure. This is something that's very important because many other agencies or people, even scientists, they don't have any clue what is the Einstein procedure and modified Einstein procedure, let alone BOR-MAP, CMAP, and so forth. The Einstein procedure is bottom up. So essentially, you look at gravel transport, and he said, we'll have a layer for grain size, uniform grain size here. We'll have twice that layer out there, and the bed load is going to be the quantity of sediment passing that thin layer close to the bed. And it's kind of rolling, sliding, and on the bed and frequent contact with the bed. And that DS is, while bed load layer twice the grain size is a definition, and some people try to revise this and make this a flexible layer and whatnot. No, if we talk about bed load, to me, I'm old-fashioned. It's twice the grain size. It's a definition. Let's not change definitions, please. The suspended load is the amount of sediment being transported above that layer, okay? But Einstein said, I'll get an equation to determine how much sediment is rolling in that thin layer here. I'll determine a concentration near that layer, and then I'll use the Rouse equation to get a concentration profile going up, and I will integrate how much is going up. Yeah, I'll get the total from the sum of those two. This is the Einstein procedure. It works well for gravel, coarser grain, rivers and whatnot, But for sandbed rivers, it was shown not to work very well. One of the reasons is that you calculate humongous grain size and concentration near the bed, and you're going to extrapolate this thing, and you'll be off by 2-3 orders of magnitude, to the point that I remember Jack Kennedy going to a conference, and he said, if you want to predict sediment load, my friend, just predict 0, because you're sure you won't be off by more than 100%. Because if you use any of those methods, you could be off by 1,000%, you know. The Bureau of Reclamation, Colby, Embry, those guys started this on the Niobrara River, the Middle Loop. A lot of studies were to say, let's do the modified, let's do a top-down approach. We're going to go from the top, we're going to measure all we can to the depth of our sampler, and then we're going to extrapolate and find out how much is down below. Make sense, yeah? So BOR-MAP has been developed with essentially Lara and Pemberton's a scheme in mind, and it has been, actually, it was called PSANS, if I remember, and PSANS has been reprogrammed, kind of modernized there to be called BOR-MAP by Chris Johnson, I think, and Dave Reff, if I remember. Those were the two guys who worked on that, so, and it has been used. At some point, Reclamation asked us to look into this thing and say, well, can we improve this and whatnot? And I had a student, CIMA, who looked into this thing. And then we developed a new procedure called CMAP, and Drew alluded to this earlier this morning, and I want to give more details about it. So the idea, we have velocity profile log law, we'll get a concentration profile, the Rouse law, and then if you multiply those two, well, you get a power form in a log, and that's mathematically intractable, meaning you don't get an analytical solution from the power times the log. Maybe 10, 20, 100 years from now, there'll be a way to do that, but to this day, it is not. So we can still solve them numerically. So the idea at the time, and we're talking here the 50s, was to use two bins. They had two particle size distribution at two different locations above the bed, and try to find an overlap for that size fraction. And then you get 2 points on the plot of the Rouse number and the fall velocity. And from this, you extrapolate, and then you calculate a little procedure to calculate this, a numerical procedure. Well, we figured out with CMAT that there were problems with that. Drew alluded to this verbally this morning, is that in some cases, then we had only one bin, so we didn't have two overlapping bins, so that doesn't help at all. So the lines, we could pick any line you want, right? So another problem that we encountered is that you could have two in which the slope is negative, meaning that the bigger the particle, the easier it is to bring this into suspension, which doesn't make any physical sense, right? So, but I mean, because of errors and the measurements in those two bins right there, that would not work too well. So, and the third major source of error was that sometimes, and that's an embarrassing one, that the suspended load, which should be a fraction of the total, was greater than the total load. So when you calculate something greater than the total, then you say, well, it should be a part of it, and you know there's a problem somewhere, right? So therefore, what we did is to look with CIMA, develop a new procedure that would circumvent those quibbles there. And Junke Guo, who's now faculty at University of Nebraska, he's very, very smart with mathematics, and when he developed a series expansion for the Einstein integrals, the J1 and the J2. On my webpage there, you have this program, and if you want to use that, and it's just very long, inconvenient series expansion of the Einstein integral. So you do, after geometric series, and then you integrate every single term, and then you sum this sum and so forth, right? So, but anyway, it works real well. And then you're going to get into a heavy math here. Of course, professors always like to do this kind of thing, but you find essentially the J1 and the J2 from this. And the key of what we did here, and you will see things simplify greatly after that, is that we can look at the ratio of the suspended load, what is above the bed load, to the total, because I can integrate to the bed layer, and I can integrate all the way to the point where the velocity is 0. Take the ratio of those two. If you do this, you get a simple relationship, because you have only two parameters, the Rouse, and you have H over D, so the ratio of flow depth to the grain size. And the other integrals then, of course, will vary, and we'll get series of lines for different H over ds. And the E is the ratio of the bed layer to the total flow depth. So in kind of dimensional form there, E may be 5%, so 5% of the total depth or so, or 1% or 5 or 10, you know what I mean? So this is the E, so it's really 2ds over H. So now you get a simple graph, and it's quite amazing that for different H over ds, you get a single graph like this. That may be the part that may be applicable for you guys, is that the Rouse used to be the way of doing things. When I was a student, we always used the Rouse number, you know, fall velocity, omega over beta S kappa U star. So we need the von Karman constant. We need correction factor beta S, which turns out to be 1. So it's really omega over U star. But me, I use the inverse of this thing, which is U star over omega. The shear velocity that's applied, hydraulics, ratio square root of tau over rho, so square root of GH and slope. So that's real easy. You need the flow depth and the slope. So that's all you need. And omega is the fall velocity of your particles, which depends on the grain size. So then grain size, you can calculate the fall velocity of those particles and get the ratio. And if it is 1, that's what I love. 1 here, you get 40% in suspension and 60% as bed load. So here's the way to think about it, the way I think about it, which simplifies my life greatly, because sediment transport can be a nightmare, really. So you calculate your shear velocity. Shear velocity is a measure of turbulence, right? So how things move. So you get a certain scale for the vibration of the fluid itself, okay? That is our U star, okay? The fall velocity is the velocity at which the particles settle down. If it's a little particle, it takes forever to settle. Big particles, it just drops very quickly. When the ratio of those two is about 1, yeah, you get about the same proportion of bed load. Let's say 50% would be exactly 1.2, 1.3, something like that. But you get equal parts as to how much is bed load and how much is transported in suspension. Does that make sense? Yeah. So now I got 3 zones. I got this, looks like a flag or so, but you get a zone if it's less than 0.5 or so, then you know 20% is in suspension and 80% is on the ground. So I look at this like the dog and the tail of the dog. You want to find out where the mass is. Well, you got the dog in the bed load and the tail in suspension, right? All the big mass is really at the bottom. Make sense? Yeah. And if you go above 2, which is another nice number, so 1/2 and 2, now you get to 80% is in suspension and 20% is the dog. Make sense? So 80% is going to be in suspension, so all in suspension, and you get 20% that's going to roll on the bed. Make sense? So that is very easy predictor to find out what kind of method you need to go to the river for sampling. Yeah. If you're in this zone here, what kind of sampler are you going to use? All the sediment is rolling on the bed. You need to get a bed sampler, get a sediment trap, get something that's going to collect a Haley Smith, get the material that is rolling at the bottom, because that's where the dog is. Make sense? Yeah. And if you're on the right-hand side above 2, then no, the bulk of the sediment is being transported in suspension. So now you need to go there with your depth integrating sampler or point sampling and so forth. Does it make sense? So it gives you an idea. Very easy. So you know your river, you can easily calculate your shear velocity. And for a given grain size, you'll find out whether most of it's in suspension or rolling on the bed. Yeah. So that's the first part here. The second part is really using a sampler. So a depth integrator is therefore CMAP is going to be series expansion from the Juncker-Guos approach, and then modified Einstein because we go from the top down. Does it make sense? And so modified Einstein procedure, and the 1P is going to be for depth integration as this little demo came here. Actually, I should have kept, layer a little higher because it's confusing with twice the grain size. My grain size should be graphically a little smaller here and get the nozzle a little higher or something like that. But you see, you'll measure all the way to the nozzle when the belly of your sampler hits the ground, where the nozzle is, which is typically 4 inches, 10 centimeter above the ground. So you measure from 4 centimeter all the way to the free surface. This is your measured load. The unmeasured is what's passing underneath. And you want to estimate how much is passing underneath the unmeasured load that is not accounted for. And CMAP with the two P's is really for other samplers. When the rivers get too deep, you cannot use a depth integrator. So like the Mississippi, you have to measure by point. So you get point measurements. Therefore, the second P in CMAP, you make 1 point sample, you're going to go, let's say divide this in 10. This is 10 feet. You're going to measure at 9 feet or 1 foot below the surface, 2 feet below the surface, 3 feet below the surface, and so forth. You'll collect until you get to the bottom. You get point measurements, and then, you can recalculate all the concentration times velocity and so forth. You recalculate your sediment load from that, and you get the measured load, and you want to predict the unmeasured load. Okay, so how much do we have to correct the measurements for? I want to mention here, this is the work Seema. She's now at Cal Poly. It was Seema Shah when she did her master's looking at BOR-MF. And we published papers about those things and the ratio of measured to total sediment discharge. And so we get the same thing here. Now that's the ratio of what you measure to the total. Yeah. So now the measure will never be greater than the total. Yeah, that's impossible with this method here. And you get the same type of relationship as before, h over ds, the e again, the Rouse number, and those integrals that are a function of the Rouse number. So, okay, so we get one graph here, which is the one I want to show. U star over omega or the Rouse, I like U star over omega myself personally. If it's less than 1, forget the Einstein procedure. You cannot use the Einstein procedure for that. You must use the modified Einstein. If it's greater than 2 or 3, then what you're going to measure is going to be the bulk of all the sediment. Does it make sense? Yeah. So for a grain size of 0.2 or 2 millimeter, which is about typically what you measure in sand size fractions, those two lines are very close to one another. So you get kind of universal graphs here. And that is the ratio of the flow depth to the sampling depth. The sampling nozzle here, which is 10 centimeters. So essentially, this is twice you measure really, you get 20 centimeter and your nozzle is really halfway down. That is the worst case scenario in a way, it's a very shallow stream. Yeah, so if your nozzle is 10 centimeter above and you get 10 centimeter of water above your sampler, to integrate over this little here is not a big deal, okay? But rivers will be typically a lot deeper than that. And now you're going to measure a large fraction of the total, and that's what this is for U star omega greater than 4. And that is, you're going to measure the bulk of the sediment transport in that river. If you're in this zone here, you're wasting your time measuring from the top down. Using modified Einstein is a total waste of time. Use a Helly Smith, use a sediment trap or something else in your stream, because it's all bed load, right? So a bit of theory, which doesn't hurt too much. Seema, of course, tested this in the US, and she got pretty good agreement there. And Inouye was studied by Albert Einstein, actually. In the Mississippi, all the way to the Mississippi, we got data there from the Corps working at the Old River Control Complex. So, yeah, good agreement here. Of course, at the time we did comparison with BOR-MF and whatnot, and our results were good. I suggest that you look into this because you're going to circumvent a number of problems that were, lingering from the old Colby and Hembry approach. So years ago, this is kind of a case study or an example here. We had a project in Korea with K-Water for about 3 years there, maybe 5 years ago or so. And we got all the data from all the rivers they did in Korea. And it relates a bit to what we talked about this morning and how to estimate the sediment load in rivers there. So essentially, you get your hydrographs all the time. You can get a flow duration curve. They measure mostly depth integration there. And then you get the sediment load from that. You're going to get a rating curve. You get concentration versus discharge for different streams and so forth. So if you combine the sediment rating curve with the flow duration method, you're going to predict the sediment load, the mean annual sediment load of a river. This is a standard method that dates back to probably the 60s or maybe the 50s, where things were being done by hand. at the time. Nowadays you can automate and calculate all the time with computers and whatnot. So we could get the sediment load for all rivers at all times and so forth. So that's the idea of getting the sediment yield directly measured in the river. So from this, we get the total sediment discharge. And then we looked at the comparison for the map of all the locations. So they had a big project there called the 4 Major River Restoration Project, which I'll talk about tomorrow. But they had a big collection program there for a number of years. The Nakdong River is coming here. The Han River is coming here. The Han is hooking back up. And we compared MEP and CMAP. And, the CMAP is here in the green dots. And look at this here. We're 1, 2, 3, 4, 5, 6 log scales here. So you're going from $1 to $1 million a day, or 1 million tons per day is here. 1 million tons of sediment per day. You're going to shovel for quite a while to carry all this sediment load here. And the problem with the MEP, and that is not the BOR-MF, so I don't want to put this on BOR-MF here. They use an older version, which is probably good dating back to Colby and Embry, which they programmed themselves and whatnot. But in some case, they got errors there. They calculate an outlier way out there, I don't know, 4 or 5 log cycles. And just one point like this can disturb your whole data set. You don't see this. You have tons and tons of data on your spreadsheet right there. You get 10,000 points, and you'll get one point that's 10 to the 25 or something. That when you get the sum and all that stuff, then, it's going to mess up all your database.